Okay, so I promised some proper videos, so here we go. So this is to continue some of my maths video series, and I'm just going to start with sort of how to solve simple second order differential equations. And I'm going to split this video because there are certain topics that are best segmented in this case. So the first thing I'm going to start with is a general proof about how to solve a linear second order differential equation, and then we're going to increase the complexity of the different cases. So this is just a straightforward second order differential equation in the form of some constant a times d squared y dx squared plus some constant b times dy over dx plus some constant c times y equals 0. So this is a differential equation that we're trying to find a general solution to. So the way to do this is to first, I put guess in inverted commas, a solution of the form y equals e to the lambda x. I mean, the reason that we guess an exponential solution is because exponential functions have this very useful property that you differentiate them over and over again, and they basically retain the original form. So the differential of the derivative of e to the x is e to the x. So the fact that you can differentiate them over and over again and you get something quite similar means that they're always a good place to start, because an equation like this, you're going to end up with a bunch of exponentials that you can sort of convert into an algebraic equation. I mean, that's the reason for it, sort of converting a differential equation into an algebraic equation, and the fact that these exponential functions have the property that you can differentiate them over and over again means that they're a very useful starting point. So the initial guess is y is equal to e to the lambda x for some lambda. So the way that we do this is we first substitute it back into the equation. So all I've done is taken e to the lambda x and stuffed it back into this equation. So we've got a times lambda squared, the lambda squared coming from differentiating this twice, so the lambda comes down and it comes down again, so we've got lambda squared e to the lambda x plus b lambda e to the lambda x plus cy is equal to 0. So the next step is to factorise out this e to the lambda x term, and then we can see that we've got this e to the lambda x times by this thing is equal to 0. So that immediately implies that there's two solutions, that this thing in the bracket can either be 0 or this thing can be 0. If we say that the exponential part is 0, then that's the trivial solution. So e to the lambda x, which we've already defined to be y, is equal to 0. So y equals 0 is our first trivial solution, and it's trivial because, I mean, you can, if you let y equal 0, then obviously this is just going to be 0 plus 0 plus 0 equals 0. So that's considered to be the trivial solution. But we want the more general solution that isn't just y equals 0. So that's this second solution here. So our non-trivial solution is a lambda squared plus b lambda plus c is equal to 0. Now, of course, this is our algebraic equation, which is also a quadratic equation. It's got a coefficient of 2 here. Obviously, we know how to solve quadratic equations. We can simply use the quadratic formula to solve it. But we can also do it by completing the square, which is just this method below here, if we don't want to use the quadratic equation. So simply we have our equation here. So taking a factorising a out, the sort of coefficient of the squared term is always the most difficult to handle. So we factorise that out, and we have lambda squared plus b over a lambda plus c over a is equal to 0. And then inside the brackets, all I'm doing is completing the square. So lambda plus b over 2a squared. So the way to complete the square is you simply take the coefficient of the linear term and divide by 2, because then of course you can imagine you have two brackets, and then these two terms are going to add together to give you your b over a term. So you divide your linear term by 2 and put this to be squared. But then of course you're going to also generate this b squared minus 4a, which you don't really want, so you're going to have to take that off. And of course all you have remaining is your c over a. So you complete the square. The next step is to divide by a. Now people always tend to do this too quickly, in the sense that we have to carefully consider what we're doing. When we divide by a, there's an implicit acknowledgement that a can't be 0, because of course you can't divide by 0 So if the point at which we divide through this equation through by a to get rid of this a here is the point that we acknowledge that this is not this is only a general solution for cases where a is not equal to 0, which is fine, because we're gonna be solving our differential equation for the d squared y over dx squared term anyway. This is a second order differential equation. If a was 0, then it would only be a first order differential equation. So this is fine. So again, we have a percent acknowledgement that a is not equal to 0. Again, so then all we have to do is simply rearrange what's left. So we take this lot onto the other side, square root. And again, when you square root, you need to think carefully about what's happening. That every time you square root, there's going to be two possible roots. There's going to be the negative and the positive root. So I put the plus or minus sign here just to illustrate that there's two possible solutions to the square root. Again, and then just taking the b over 2 onto this side. So again, here we go. We have our lambda, and then again, this is our original differential equation. And remember, we made our assumption that the solution was y is equal to e to the power lambda x. So we now know, given that assumption, what lambda is, and there's two different lambdas. There's one for the positive root and one for the negative root, and this lambda. So our general solution is y is equal to e to the lambda x, which is, and we've worked out lambda, our general lambda. But again, there's two lambdas, because there's our positive root and our negative root. So what we can actually do is we can add these two together. The reason that we can add these two together is that, remember, this equation, our y is equal to e to the lambda x, when substituted into here, makes 0. So this negative root makes 0, but the positive root makes 0 as well. And 0 plus 0 is equal to 0. So you can always add these terms together. There's nothing wrong with adding 0 plus 0 is equal to 0. That's the sort of intuitive way to think about it. The more rigorous way of thinking about it is that these equations are linear. So of course you can sum these solutions together. That's perfectly valid to do. So our general solution is our y is equal to e to the lambda x, our negative root, plus e to the lambda x positive root. And so all I've done is I've substituted the positive and negative root into here. So this is the general solution to our basic second order differential equation. Now, in the next video, I'm going to introduce a complexity called the degeneracy, which is in the case that when we get to our quadratic equation, which is here, a case where instead of there being two solutions, so a positive and a negative root, there's only one solution, and that's slightly different the way you have to handle this. So that's done for now. Thanks for listening.